Okay, this is a three-phase power problem. So you're given a three-phase load. You're told that it's the voltage, the line voltage is 208 volts RMS, and the line current is 73.8 amps RMS, and you're told that the load absorbs magnetizing VARs, a term that I don't like that much, but basically that means that the power factor is lagging, and it means that the phase angle between the voltage and the current is greater than 0, and it's inductive. It tells you all three of these things right here. So theta sub phi is the phase current between the phase shift. The theta sub phi is the phase shift between the voltage and the current, and it's positive, which just means that it's inductive load. And you're told that the total power of the load is 22,659 watts. So it's nice to draw a picture, although you could get by without drawing it, but let's draw a couple of pictures. So first of all, there's a source, and there's 3 wires going over to a load. Okay, there's 3 phases, A, B, and C, going to this load, because just from the way the problem is described, you're told that it's a 3-phase load, and you're told this stuff. So like this is V sub L in here. It's V sub L. It's one of the the line voltage, V sub L, the line voltage, or line to line is the terminology. When they talk about line voltage, they're talking about line to line. And when they talk about phase voltage, they're talking about line to neutral. So you're given the line voltage V sub L, just one of these. The magnitude of one of these is 208. And then there's a current in one of these guys, and you're given the magnitude is 73.8. There's 3 currents, but they all have the same magnitude, and they're just going to be off by 120 degrees, the currents. Same with the line voltages. You're given one of the magnitudes. There's going to be 3 others. There's going to be one in here, and then there's going to be one in here, and they're all going to be off by 120 degrees. And then there's some power leaving this guy. And there's also a Q leaving this guy. And those sum up to an S leaving this guy, the total. So in here, there's a Y or possibly a delta connected load where you could break this up into 3 loads where there's power, 1/3 of the power coming off of each one of these, but you're just given the total. Okay, so that's what we got. It's good to stop and kind of think about what it is reality-wise. What are we trying to model here? Because sometimes they just give you these word problems. All right, so we're asked to find a couple of things. Let's squeeze it over here so I can squeeze it on one piece of paper. We're asked to find the Q total, the reactive power, Q total, reactive power. All right, and then we're asked to find the power factor, which is really a way of asking for this angle. Okay, you're just told that the angle's positive you're being told that the load absorbs magnetizing VARs, which is a roundabout way for them to tell you that the angle's positive. But they want you to determine the angle, or really the cosine of the angle, which is the power factor. All right, so the answer to get Q here, we have this form. We'll use this formula. We'll use S sub T is 3 S sub phase, right? The total power is 3 times the per phase power. Remember here, there's a Y connected load, and there's power coming off of each phase. There's power coming off. There's power coming off of 3 phases in this Y connected load. So I'm going to hook this up. So there's that, and this is also given by root 3 v sub l I sub l now if that were a phasor, it would have angle theta sub phi. So we have all of these. We have a lot of this stuff. So we have, so we have, so this one's root 3. We've got, you have to use RMS values, and that's what we're given. This is a power formula. You need the RMS value. So it's 208 and 73.8. We're given RMS values with some angle theta sub phi. So this is 26,588 with some angle theta sub phi, and this is complex power. The units are var. So now we can draw this. Basically, we're given this big P of t, and we've just calculated, using this formula, we've calculated the magnitude S as 26,588, and this guy was 22,659, and this, so we don't know Q, and we don't know the theta sub phi, but we know that theta sub phi is positive. So we were told that, so we know the triangle goes up like that. And this formula here, it gives us the magnitude that we need. We still don't know the phase angle, but we know enough to draw this. And then, you know, Pythagoras, we know that, you know, just solving for pi, it's s squared minus p squared, right? Draw this, and then solving this right triangle here, we can get Q. So this is root 26,588 squared minus 22,659 squared. It's 13,909, and this is Q, so it has units var. Okay, now we know Q. Okay, so we could get this angle, right? So with some trig, we can calculate theta sub phi. It's going to be the arctangent of Q over P, right? Just doing, we know Q now and we know P, so this is 13,909 over 22,665. It's 31 degrees. And so the power factor is just the cosine of 31.5 degrees is 0.8522 lag. Lag just is a way of saying that it's the it's an inductive. This power factor lagging means inductive. Load absorbing magnetizing vars means inductive. To me, you just need to make a table of these absorbing magnetizing vars and generating magnetizing vars and power factor lagging leading. Make a table of when that means inductive and when that means capacitive, because it's confusing, and trying to make sense of it and memorize it is just a waste of time. All right, that's it, huh? Did we get our answers? Oh, this is an answer. I forgot to put a box on it. Anyway, all right, so some of this is just word problems. You're told these things. You have to realize what those things mean, and it helps to draw some diagrams and think about that. All right, hope that helps.